End up talking about. But now it's about to go live in any moment now. And then I'll introduce you. We're live. Here we go. Hi, I'm Meta Spencer, and today let's go to some small island states, if you will. It sounds like a very pleasant excursion to make to some places that have a lot of coastal area. The thing about an island is it's pretty far from a lot of sources of important energy. And so they have some predicaments that people in larger areas that are not islands don't have to worry about getting energy. But they do have one resource. They're surrounded by a lot of water. So there are people in this world who are very concerned about how to help developing countries that are small islands use the resources that are actually available to them for meeting their own needs. And of course, they have other problems that some of us don't face. One of them is islands are usually or often surrounded by coral reefs. And coral reefs, as we know now, are dying because of the heating in the oceans. Well, what can be done about that? There are very few things, frankly, that look as if they might be able to solve the problems of these poor, beautiful little critters in the ocean. And I'm going to interview two people today who have some experience in working with small islands and the problems thereof. One of them is Dr. Tom Goureau, who is the president of the Global Coral Reef Alliance, which is a nonprofit organization for coral reef protection and sustainable management. And he's a coordinator of the UN Commission for Sustainable Development Partnership in New Technologies for Small Island Developing States. And the thing about Tom Goureau is that he's a real diver. He claims that he has dived longer and in more coral reefs around the world than any other coral scientist. His father was the world's first diving marine scientist, and he grew up swimming in coral reefs as soon as he could walk. So good morning, Tom Goureau. How are you?
It's a pleasure to be back with you on this program, and glad to talk about the oceans.
Well,
yes,
I'm gonna grill you in a bit, but first let me introduce
Sure.
Dr. James Baird, or Mr. James Baird, who is the author of some very bold claim that he's published a book called Thermodynamic Geoengineering. And this is an important piece of work, but it's based on a principle of physics that is way beyond my pay grade, as they say. I don't know much about geoengineering, period. I'm all in favor of it. I'm promoting it the best I can because I believe we're at the point where absolutely we better get going on something. But thermodynamic geoengineering, I don't know. That's somehow you're going to take the ocean's temperature. By the way, I do know that the oceans are stratifying in terms of temperature so that the top layers are getting much warmer than the bottom layers. And there are some problems that arise from all kinds of stratification of the ocean. So I gather that's going to be a topic. Jim Baird, say hello to our guests, and I want to greet you.
Good morning.
Good morning. I hear you live in Nanaimo, so say hello to all my friends in Vancouver Island. Okay, so now let's get busy. I'm going to start with Tom Goureau because I already know Tom a little bit. And I absolutely don't know what you're all about, Jim Baird. So you're going to have to use your prepackaged video, I think, to give us some technical explanations. But in the first place, Tom can explain what you are all about, which is a little different from what he is all about, although you're both concerned about how to help small islands. Is that right? So Tom, tell us first a little bit, if you, or however much you want, about your own specialty, which is, I believe, biorock. I know a little bit about that, but I want to know a lot more. And then go on and begin to give us an introduction to Jim's specialty, if you will.
Okay, it's a lot to cover. Well, I'm from Jamaica in the Caribbean, and I've been diving all my life since I was, basically since I could walk. I've been diving and swimming in the reef. And my father and my grandfather were divers, and they began diving in the 1940s in the Marshall Islands of Bikini Atoll to document the health of the coral reefs. And they were the first people to do that. So we've been doing that, all over the world continuously since the 1940s. And anyway, so they've long passed away, but it's what I continue to do because I have the largest and oldest collection of pictures of how things used to be. And you could cry to see any of these places now is basically what it boils down to. In most places, the people who call reef scientists have never seen a healthy reef. They have no idea what they used to look like. They're just seeing the last dying remnants. A handful of places still left in good condition, but we've seen most of them disappear in my lifetime. Almost all have disappeared. And the handwriting's on the wall for almost all that's left for a lot of reasons. And that's because they're the most productive of all ecosystems in terms of the amount of biomass they produce, the biodiversity per unit area, of anything in the ocean. And they just excel in terms of biomass, carbon storage, productivity, all those things in a very tiny area, less than 0.1% of the ocean. And it's not like rainforests that cover a large part of the earth. This is like less than 0.1% of the ocean. So they're only in shallow water because they need light. Corals need light, so they have to be shallow, clean water.
You say 0.1% of the ocean?
Less than 0.1%, yes, because you have to have water that's shallow and clear. It can't be muddy, it can't be too hot, it can't be too cold, because they're the fussiest of all organisms about demanding perfect environmental conditions. That's what they need. And when they have that, then they recycle everything. So nothing gets wasted. They pretty much, so they're extremely efficient. That's how they live in the deserts of the ocean. Tropical waters are the clearest of all, because there's no nutrients. There's almost no phytoplankton in them. Okay, so and that's where coral reefs live, and they do that by not relying on a lot of garbage coming into them from outside or food. They do it by recycling what they have, but they are dependent on the outside. But at any rate, we'll watch them disappear.
And I'm kind of so surprised that there's such a small percentage of the ocean now.
Yes.
But because what I had heard was that the rest of the ocean and we are often dependent on these corals.
That's right. That they're hundreds of times richer than the rest of the ocean in terms of biodiversity per unit area, productivity per unit area, all of those things. I mean, they have a quarter of all the species of fish in the sea, or 25%, in less than 0.1%. So that gives an idea, but they're off the scale in every regard. But they're also the most vulnerable of all ecosystems because they require the cleanest waters. So if it gets too muddy, people cut down the rainforest and let the mud wash into the sea, the reefs die. If they don't treat their sewage and let their nutrients go into the sea, that becomes fertilizer for algae blooms, what we call eutrophication, that smother and kill them. So that's happening in every populated coastline of the world. Where you're near people, there's sewage, there's fertilizer going to the sea. And where you used to have reefs, now we've got big masses of weeds and slime and stuff that has no value. It's replaced not only the reefs, but the whole ecosystem that was there. In cold waters, we've lost the oyster reefs and the mussel reefs that used to be there. So I mean, there's several issues there. But anyway, we're seeing collapse of all marine ecosystems, as we know. And so that's one issue. Now, the blue economy is a big sort of almost a mantra. All countries declare they're going to have a blue economy, Canada among them, and rightly so. But the thing is that we're killing all our coastal ecosystems. That's a place. Every place, if you dive anywhere and knew how it was 50 years ago, you could cry. It doesn't matter where in the world you go, And so there are a lot of reasons for that. I mean, as we know, everyone is most aware of overfishing or over extraction, the collapse of the cod and the Grand Banks and all that. It's this utter catastrophe. It's never come back, even though they pretty much wiped it out. It's just not coming back as people had hoped. So, and that's an example. They wiped out what was the richest fishery in the world, but we're seeing that repeated in every fisheries. That's what's happening. So when I was a boy in Jamaica, we had huge groupers, 200-300 kilogram groupers at the bottom of every reef. And my father saw them. They were friendly, would see them on every dive. But as soon as he taught other people to dive, they went back with spear guns. And we never saw them again. They were wiped out, gone forever. And that's happened, in every ecosystem, mostly because before people recorded what the big fish were, but mostly by the time people were there making any measurements, they've been fished out. And it's like the big game on land too. So definitely, overfishing has been out of control. It's causing the top-down collapse of these ecosystems. But at the same time, every global fish is collapsing from the bottom up for a lot of reasons. Okay, and that is to say that they're fueled by nutrients. And so in many cases out in the open ocean where it's clear blue water, there are no nutrients. That's why the water is so transparent, So those places could benefit from a bit more nutrients. But if you add too much, what happens is the weeds take over and wipe out everything that was of value. The oyster reefs in cold water or mussel reefs, any place, you get basically a handful of worthless weeds that just smother everything else because they're most able to suck up high levels of nutrients. So we're seeing almost all coastal zones go that way. And it's extending beyond that now because a lot of people want to fertilize the ocean, but the thing is what that will wind up doing is creating dead zones in deep water. Okay, now, dead zones didn't used to be a problem. When I was a boy, I saw what was probably the first dead zone in the world that was documented in Kingston Harbor, Jamaica. When I was a little boy, we had coral reefs inside of Kingston Harbor that I swam in as a child. And in the space of about 2 years, the whole harbor went anoxic below except for the very surface area where oxygen could be mixed in. It's just, hundreds of years of sewage and garbage and everything going into an enclosed body of water. And from 1 year to another, it went from having live clams and worms of all kinds on the bottom of the harbor to being nothing at all. Just all the oxygen disappeared, mass mortality. And so the fish only swim in the surface where there's, some air mixing from the air above. So we saw that happen. A Jamaican marine biologist, Dr. Barry,
let me get clear about one thing. And that is, I've heard you're talking about dead zones, and I'm not too familiar with the term, but I do run across the concept of that there are areas of the ocean that are deserts. And those, when they refer to that, they usually say that they're deserts in the sense that there's not much life going on there because there's an absence of iron. Now, are we talking about two different things here? What you're calling?
Yes. Because I mean, in a sense, you see, coral reefs occur in what we call the deserts of the ocean, the blue water that has so little nutrients and it doesn't have much productivity.
Those areas, deserts, sorry, but now you're saying something interesting. That
in the remote ocean, in large areas like that, and coral reefs are sort of adapted to those conditions, the low nutrient conditions. Now, when you get too much nutrients, then what happens is you get bursts of productivity, mostly small phytoplankton, and many of them harmful algae. I'll come back to that a little later. But those bloom, and then they settle to the bottom in large amounts and rot. And when they rot, the bacteria use up all the oxygen in the water. And then when there's no oxygen in the water, no other forms of life above bacteria can breathe. So they all die. And that's what you call the Z zone. The clams, the worms in the mud, the fish that are lying above, all of them just die. They go belly up and the whole place stinks of hydrogen sulfide. So these dead zones used to be very rare.
Hold on. Now you're triggering some more questions for me. So I'm taking you off your line of thought, but I've got my own line of thought, because I got worried about something about a couple of years ago when I interviewed Paul Werbos and Peter Ward, who is the guy who wrote a book has written a lot about previous extinction events.
Oh, yes, that's
and
right.
His claim is, their claim, as they discussed it, was that these extinction events had all been the result of large emissions of hydrogen sulfide, or what I guess we call swamp gas, from the bottoms of the oceans, and that this occurred because the oceans became stratified, and because there was an absence of oxygen in the bottoms of the ocean, and that there are little critters called archaea, maybe mispronouncing them, who create hydrogen sulfide, and that we are in danger of creating a new extinction event by doing exactly what you've just been describing.
Yes, that's right.
Now, are you talking about the same kind of thing?
Well, it's a similar mechanism. Again, in the past, I mean, there were cases where the ocean went anoxic for other reasons, lack of circulation, lack of turnover, and meteorite strikes, volcanic explosions producing sulfur gas. So there's a lot of causes, and some of those extinctions were in fact linked to oceans that went anoxic, either as a cause or as a result. So that there's a couple issues there. But we're doing that now on a large scale. Essentially, our ocean had very few what we call dead zones. These dead zones are not deserts of the ocean. These are zones that have no oxygen, so no higher life can live in them. And they smell of hydrogen sulfide. They stink of rotten eggs. So that's what's distinctive about those habitats. So now, we would have them under areas that were very productive, where lots of phytoplankton settled down. But for example, the mouth of the Mississippi River, all that fertilizer running off the Iowa cornfields flow out into the Mississippi. It causes huge blooms of algae. And then the algae, when they rot and fall to the bottom, the oxygen disappears. So all the fish and clams and shrimp die in the waters. They have no oxygen to breathe. So, and that's spreading year by year. But it's spreading worldwide. We're seeing that in many coastal zones. Now, if that was to happen on a very large scale, then organic matter would accumulate there, and that would, be removing CO2 from the atmosphere in the long run. And that's, in fact, basically how these anoxic zones are how the Earth got rid of excess CO2 when there were mass extinctions caused by high CO2, which is many of them caused by, high CO2. So that gradually got removed because the ocean went anoxic. It got so hot that the surface water got too warm. It wouldn't mix down. The deep water didn't circulate. It went anoxic. And at that point, organic matter rotted and piled up. It couldn't decompose. And then eventually, over the course of hundreds of thousands of years, the excess CO2 was removed and buried in the sediments. And then, a few million years later, new coral reefs could evolve. That's happened several times in Earth history. So coral reefs are an indicator of those. And I tell you,
just a minute, because I'm hot on the trail of this thing. Now, you're not saying that these dead zones that you're investigating are likely to become big enough or serious enough with this hydrogen sulfide emission to actually create an extinction event now?
No, we're not. No, we're not. We're basically at this point, they are patches in coastal areas that get a lot of sediment and organic matter and nutrients flowing from rivers, from cities, or every place, so big populations on the coast. That's where we're seeing dead zones appear. So it's in the shallow coastal zones, which are the most productive. Those are the areas being affected. But in some places, we're seeing it in the deep sea. I'll give you an example. there's a lot of salmon farming. Most of the salmon people eat are grown in farms. Most of these are floating salmon farms. They have them in Canada, Nova Scotia, and British Columbia. They have them in Norway and Scotland and New Zealand. And Chile is the world's largest now. And I just did a project, a floating salmon farm in Chile. And what's happening under these things is all the rotting food that they dump in, constant flow of food to these things, manufactured material that's very expensive to produce, has high embedded CO2 and all that. They're not eating wild fish. They're eating pellets that are constantly fed to them in an industrial process. And most of that falls to the bottom. Okay, I was watching video of the salmon. Salmon eat only a tiny fraction. Most of that stuff goes down. Then there's all the salmon excrement, okay, and all that goes to the bottom. And if you were to dive to the bottom, you would see a 40-foot black pile of rotting dead material. It's overgrown with white material because those are bacteria that are consuming the hydrogen sulfide coming in from all this anoxic mess. Now, as these things build up in the fjords and in these places, what's happening now is that's creating dead zones in the surrounding water. The water's, oxygen stripped out in the sediment, but consumed from the water. And then those dead zones then kill mussels. Huge clam beds in Chile have been killed. Chile fjords have the only cold water, shallow water coral reefs in the world. 20 kilometers of them have been killed by the salmon farm effluents first. And then they're causing harmful algae blooms. The harmful algae blooms are the toxic microscopic algae that when there's a lot of nutrients, they take off. And these things secrete toxins, so those wind up killing everything in the water, shellfish, fish, everything that's in that water can die. So those are becoming more and more common too. So we're really doing a number on our coastal zone. Let's put it this way. And I mean, the only point I want to make here is that to solve this problem, we're not going to have a blue economy if we keep killing all our marine resources. We want to have them. We've got to be growing stuff back and using sustainable energy to do so. And with the ocean being 70% of the Earth, that's a huge imperative. But right now, we're mismanaging both the ocean and the Earth. And a lot of the mismanagement of the ocean is caused by stuff coming from land. So, the stuff we're dumping. We have the technology to reverse that. And I want to come back to that. And that does relate to sustainable energy, and in particular ocean energy. And we want to come back to that too. But let me say something about global warming a bit at this point. Okay. And that is that the CO2 and other greenhouse gases we'll put into the atmosphere have created this imbalance of heat. It's like more than 2 watts per square meter constantly of energy rising that's coming in and not going back out. The whole planet is warming up because of that huge imbalance, and we haven't felt it yet. We haven't felt it yet because about 93% of that heat is disappearing into the ocean. Okay, now some portion of that is melting the ice caps. That doesn't raise the temperature. As long as ice is melting, the temperature doesn't increase. It's only when it's all gone that the temperature starts going back up. But anyway, so we've got the planet is heating up without the temperature increase as long as there's ice to melt, at least in those areas. But and then the land's warming up a little bit and the atmosphere a little bit. But it's said that if all the heat that went into the ocean had gone into the atmosphere instead, the temperature would have risen to like 38 degrees C. Okay, so what's happening is going into the deep ocean slowly. But what happens is that the fundamental fact you have to know about the ocean, it takes about 1,500 years to mix. It's turning over. Okay, and that's where this comes back to that issue that you raised. It's changing with global warming. That is the temperature distribution. So what's happening is that the surface water is warming up. The warmer water expands. It's less dense. It floats on top. Okay, and if it's fresh water, the same thing happens. Okay, but to mix the ocean, basically, you've got to have a place where water gets dense enough to go down. That's what's driving the whole system. It's what they call the ocean. There's a couple names for it. There's a new acronym that's popular, but the ocean turning over, Atlantic Ocean turning over, for instance, which people say is grinding to a halt. Okay, slowly reducing, and people are saying that in another couple of decades, would stop entirely that mixing. And that's
That's what
because,
they call thermohaline currents.
yeah, the Atlantic overturning meridional circulation, AMOC, I think, yes.
Okay.
So, but that's, and so people are concerned about that. They're not necessarily correct, but I mean, the key point is that the surface water is getting so warm that the nutrients are in the deep water. You understand, the nutrients are removed by the phytoplankton. They fall to the bottom, decompose. So the bottom water is full of nutrients. It's very cold. It's very cold because the whole deep ocean has been chilled to the freezing temperature. It's 4 degrees C is all the bottom waters. And it's been chilled by cold water coming down, mostly in Greenland from the Arctic, but also from Antarctica. A couple places. There, the water normally gets so cold, it sinks to the bottom, and that drives that mixing of the whole sea. But now the water there is getting too fresh and too warm to sink. And so it's no longer able to do that mixing. And that if that happens, I mean, then what will happen is the heat won't be mixing down to sea, it means it'll accumulate at the surface faster. And so because it only takes a small change in the rate at which a slowdown in the rate of heat mixing into the deep sea for the surface to start warming up very quickly. And that fluctuates from year to year because the mixing events are not really predictable. A lot of it is driven by storms, okay? And a lot of it, especially around Antarctica, too. That's another key area because the wind there, the currents blow right around the world and they get squeezed between South America and Antarctica. And they hit deep sea mounts that cause huge amounts of vertical mixing. And those areas are also changing. So we're seeing, slowdown of the ocean circulation. Now, that doesn't mean the Gulf Stream will end, which a lot of people seem to think, because the Gulf Stream is not driven by the density mixing of the ocean. It's driven by the rotation of the Earth. Okay, and as long as the Earth is rotating, there is going to be a Gulf Stream. But this is a different story. So there's mixing for other reasons. But what we're seeing in many parts of the world now is that a lot of the fisheries depends on upwelling. It depends on seasonal events where the winds pull cold water up that's rich in nutrients. Deep water gets sucked up to the surface. The phytoplankton bloom, the fish get happy. All the productivity of Peru is famous for is based on that kind of upwelling. During an El Nino, the upwelling stops and suddenly the fish populations collapse. So what we're seeing
now, wait a minute. You said something interesting. During El Nino, this happens. Explain that.
Well, normally the waters off Peru and Ecuador and Chile are cold. And that's because the winds are blowing over South America. They're pushing the surface water away from the coast. And they're sucking up deep cold water. And that's the end of the global pattern of ocean circulation. That's where the highest nutrients, the lowest oxygen is the East Pacific, the Northeast Pacific from, Alaska, British Columbia, all the way down to Chile. Those waters are sort of the oldest deep waters in the world. So they're the richest in nutrients. So when they get pulled up to the surface, you get these huge blooms. Okay. So then the blooms are so big that they cause anoxic dead zones in the sediments beneath them. Okay. Now, when it gets very hot off Chile, which is an El Nino, then what happens is the water becomes so warm that the upwelling can't reach the surface. Okay, this is a massive warm water sitting in the way. So the phytoplankton starve, the fish starve, the birds starve, the whole productivity collapses. Okay, now we're right now halfway into El Nino. What happened is we got a I follow it every day, the temperatures in the East Pacific.
This is La Nina.
No. We're halfway into an El Nino. We've had a very prolonged La Nina that went on for about 3 years, which was really exceptional. And then suddenly about a month or two ago, it suddenly switched into El Nino mode and warmed up very rapidly in the East Pacific. And the East Pacific now is very warm, but then it stalled. It stalled halfway. And it could go either way at this point. There's no good models to predict what will happen. So, but basically, it's very hot off Ecuador now, and we're halfway there, but we're not sure yet what's going to happen. So, but the thing is, what is happening is that, remember, because of global warming, El Nino produces these irregular oscillations that are not very predictable, that affect climate worldwide, but they're on a rising baseline. So on the average, each El Nino is hotter than the one before. And the last ones have all been records. I mean, they've caused catastrophic bleaching mortality in reefs around the world. I mean, right now, Florida is going to lose most of their corals, Cuba and the Bahamas in the next week or two from bleaching. And most of the rest of the Caribbean probably, but it's just beginning to bleach in most of the rest. Now, a large areas of the Pacific could be affected. If this does develop into full El Nino, which we don't really know if it will or not, but is likely to, then we're going to lose most of the corals left in the places that are affected by El Nino. Not every place, by the way, is affected in the same way. Some areas get hotter, some areas get cooler. There's a mixture, but there's a lot of areas are affected. And we've seen mass mortalities of corals in all of the last El Ninos. So that's been, and in some cases, I've seen reefs in the Maldives, places like that, where 99% of the corals died in about a week or two, because the water was too hot for them. So coral reefs can't take any more temperature. They're at their limit. We've lost most of them already. The handwriting is on the wall with the next El Nino, whether that's going to be next month or next year. And so there's a lot that, if we're going to save not only the biodiversity, but also the people who live off of it, and then that is to say the beaches, the ecosystems, the fishes, and all that. And then we have a lot to do. So I don't want to explain a bit. I don't want to say it's hopeless. We do have a technology to solve that problem. So maybe I should jump into that and electricity.
Yeah, let's talk about BioRock and thermal.
Yes,
whatever.
right. So what we do with BioRock is, living rock, living stone. So here's a piece of BioRock. Okay, This is, as you can see, is a metal bar here in the middle, a piece of reinforcing bar. And this is limestone rock, like what the pyramids are made out of. And this is about 2 to 3 times harder than ordinary concrete. And we grew this in the Maldives, and this is about 2 years or so of growth. Okay, we get material like a lot, harder than concrete, but only if we grow it less than 1 to 2 centimeters a year. What we do is we make structures out of steel, ordinary construction steel. Now, everyone knows you put steel in the water, it's going to rust. But what we do is we apply a trickle charge of electricity, like what you would get from a 6-volt battery, trickle charge of electricity to that. Direct current. It's not alternating current. It's, very low volts. You can't even feel it, okay, in the water. But that prevents rusting.
This battery, I don't know. I don't even understand batteries how big a battery is that you need to use for that? Well,
it depends how big it depends how big a structure. We don't use 6-volt batteries. We use other power sources, such as solar panels, for instance, because a 6-volt battery would have to, every time it ran down, would have to take it out and change it, and that's inconvenient to do. So, but it's not.
A 6-volt battery is compared to, let's say, what's in my car.
That would be a 12-volt battery. A 6-volt battery, what you'd have, I guess in a small lawnmower maybe, or a small motorcycle. They're less and less common now. But but it's in the range of batteries you use in everyday appliances that you wear, your watches and so forth. So computers are mostly running on 9 volts, and they convert the alternating current to direct current. So anyway, but the point is that this is direct current. It's not alternating current. It's extremely safe and low, but it prevents rusting of the steel. Then the next step is the electrical current actually breaks down water. Water is hydrogen and oxygen, H2O. And so the water itself, with the little trickle of electricity, breaks down to make hydrogen and oxygen. And on one of the terminals, it also grows limestone rock out of the sea. Okay, limestone is dissolved in the ocean. So it only works in the ocean because the ocean's salty and it's electrically conductive. It doesn't work in fresh water. Okay, so but there's lots of dissolved limestone in the sea, and so like a coral skeleton. I mean, there's some up behind me. Maybe you can see them behind me. But a coral skeleton, or a snail shell, is made out of dissolved calcium and carbon. in the water that it takes up and it uses its energy to make a shell of precise shape or form. And we can basically do the same thing with a little trickle of electricity. So we can make a structure of any size or shape in the sea and turn it into rock. So now what a coral reef does, a coral reef absorbs about 97%, up to 97% has been measured of all the wave energy being absorbed by a reef. It's designed to absorb energy, to extract food from the water and all that. That's what coral reefs do. And so, but they don't reflect the wave because the reflection causes erosion, causes damage. They're full of holes, and so the water goes through the reef and it loses energy going through the reef, and the organisms extract and release stuff, and it's a dynamic medium, but it's not an impact that reflects. When we build seawalls that are solid, they cause reflection. That erodes all the sand in front, and then the sand underneath, and then the seawall collapses. Then you have to build another one. Okay, so that all seawalls that have ever been built, that's a story. It's a reflection that damages and causes erosion. But a reef doesn't do that. A reef accumulates sediment and stores it because it creates beaches behind it. They're protected. So what we do is we grow reefs shaped like a reef, open frameworks of steel. This is just a little piece I hacksawed out of one that was 2 years old in the Maldives. But this reef here had several things. It grew back a severely eroded beach that had washed away by itself because it took a place where the waves had, trees and buildings were falling into the sea. We grew a reef in front of it. The waves slowed down. The sand piled up underneath it, and the beach grew back by itself. No sand pumping, no dumping, anything else. So, and then the fish all moved into the reef because it was lots of holes that they wanted. And then the next year, they had the worst coral bleaching they ever had in the Maldives, and 99% of the corals on that reef died of high temperature, and the corals we were growing on this reef survived.
Oh my goodness.
They were stronger, they were growing faster, and they were more resistant. So we do this to save reefs from global warming. It's the only method that does that, to grow back beaches that have washed away. And we could do this, in any place. In cold waters, we grow oyster reefs or mussel reefs. So it's not just coral reefs. It works with any marine ecosystem. We grow seagrasses faster. We think we'll grow mangroves faster. So we think that this is a technology that can be used to make genuine blue economies based on regenerating the coastal ecosystems and their ecosystem services, shore protection, providing new sand, being the base for fisheries. I mean, these reefs are just packed with fish once we get them going, or lobsters or whatever. We can build a habitat for octopuses. So we have a mechanism for regenerating reefs. We began doing this in Jamaica in the 1980s. We built about 700 or so of these reefs all around the world in about 45 countries, mostly in Indonesia. So we've just had a lot of students who've been into it there, but it could be done every place. So, but we need electricity, and that's where we come now to the issue of the fact that small island developing states, for example, like Jamaica, electricity is extremely expensive because we have no energy resources. All the fuel is imported at high costs. These are small economies. There are no economies of scale like they are in big countries. So you have to pay the maximum amount for everything to be shipped. Concrete, cement, shipped to an island in the Pacific is just incredibly expensive, shipped halfway around the world. So people pay far more for electricity in small islands than they do in the world as a whole. And that's what I think that Al Binga would have meant. So there's been a big push to try to develop sustainable energy. And obviously, for most small island states being tropical, the key issue is how to tap the sunshine and how to tap the ocean energy. Now, we've worked for years with pioneers in ocean energy, wave energy, tidal, turbines and all of that. And all those technologies are very interesting, but they all have difficulties because they're mechanically complex. You've got, things that are spinning or rotating or pumping or moving. And when they break, they're not simple to fix. They're very technically difficult, and they do break in big ways, the moving parts. And so they're wonderful when they work, but they stop working a lot sooner than you would like, and they are very expensive, and we don't see them being a solution in poor countries. Solar energy, on the other hand, now has become so cheap that we're down to 1 cent a kilowatt hour for operating solar power plants is coming down. So that's causing something of a revolution. Now, so I want to mention that with regard to that,
A couple of questions. Now, they can use equally well the solar energy or the wave energy or the wind for your electronic system, right?
You can use any source. We've used all of them, and we've used, in many cases, we're forced to use fossil fuel energy too, because that's what's available. But the thing is that solar energy has no moving parts, and it's coming now to the fact that it costs far less than the other things and has no maintenance costs other than
the future there is going to be solar, right?
Yes, I mean that's a key thing. I think that basically no other technology is going to be able to compete. They're all wonderful. We want to see those promoted in their own way. But the thing is, right now, for instance, we're working with the Asian Development Bank. The Asian Development Bank is developing floating solar panel projects for atoll countries in the Pacific. So, for instance, we're helping the Asian Development Bank develop growing biorock reefs in order to protect these huge multi-megawatt floating arrays that are going to power entire islands. These islands have no energy resources. When I lived in these islands, Tarawa in Kiribati and Funafuti in Tuvalu, there was no electricity because the power plant had broken down. And so now all of a sudden, they're suddenly going to have electricity where they didn't have that before. Okay, these are the first countries that are going to be flooded. So now they're going to have electricity. We're going to start by trying to grow biorock reefs, partly for fisheries habitat, partly for mariculture, partly to protect these things. But the thing with this is they can keep up with sea level rise.
One other thought is, does that stuff have any value in itself? In other words, your limestone there, could you use it for cement or something?
Yes. So originally this was invented by an architect. He wasn't trying to regenerate coral reefs at all. He was trying to grow blocks, building materials he could then use to make houses and land. Okay, then
you would use a whole block of it. You wouldn't crush it and reuse
well,
it.
That's right. Yeah. The thing is, though, that you have to go at not more than 2 centimeters a year. So if you want a wall that's 20 centimeters thick, people don't want to wait 10 years. That's why it didn't take off. But the thing is, with cheap, the cost of it depends on the cost of the electricity. So with cheap solar power, it becomes far cheaper than concrete in a lot of places and harder. Okay, so there's a real possibility if they have excess solar energy, for instance, in these countries, they never had enough energy at all, but now they may be about to be in a situation where we have that. And then in addition, if we grow it very quickly, instead of making hard material, that's slow, if we grow it quickly, we make a powder. Okay, and that we make a cement from that absorbs CO2 from the atmosphere. It turns into magnesium carbonate, which is even harder than calcium carbonate and is more than half CO2 by weight. But that would remove CO2 directly from the air itself, not from the water. We'd grow it in the ocean. So it has a lot of possibilities. These islands, in other words, that are being drowned by sea level rise could be producing enough material to keep up with sea level rise, which is now about 3 to 4 millimeters a year. But it's going to accelerate because the warming we're seeing, especially in the Arctic and Antarctic, is accelerating the melt, and it's getting close to irreversible. That means we've got meters of the stuff coming. I mean, I don't think people understand how critical it is. And I mentioned also that it's life and death for small islands, but Canada has the largest coastline in the world.
Well, let's talk about the dynamic thing. I want to know what let me invented.
Let me mention just before we get to that is that first of all, I mean, by way of introduction for Jim, is that this ocean thermal energy is a way of taking that difference between that cold deep water that was chilled and the warm surface water. So that allows you, in effect, if you can exchange heat through that, you can set up a thermal cycle that you can make electricity with at a low level of efficiency, but there's a lot of water out there. And this was understood by a French engineer called d'Arsonval. And he set up the first ocean thermal energy power plant in Havana, Cuba in the 1890s. Okay, and it worked perfectly. We were able to generate electricity from that thermal difference between the cold, deep water and the warm surface water. Unfortunately, as soon as they got it working, it was destroyed by a hurricane. And they lost all their investment. They got investors to get the new one. They built a second one on the same spot, and another hurricane took it out. At that point, they gave up. So this was proven in Cuba, 100, more than 120 years ago. So that method now, there was a gentleman who we were hoping could join us, Al Binger, who's my friend, who has been a big promoter of ocean thermal energy for small island states, and Dan Gretsch, and they're about to set up the first such plant in the island of Saint Tomé, which is in the Bight of Benin, the corner of Africa, just east of Nigeria and north of Cameroon, south of Cameroon, north of the Congo. So it's a small island that isn't a place where they've got cold, deep water and shallow water nearby. So that's going to be the first. It's going to be technically difficult because they need large pipes. They need to be pumping cold water up from above. Now, what Jim is promoting is something that's really very different than that. And that is, I think his video will show that, but this is basically a way of not pumping the water up, but pumping the heat down by using another fluid to transport the heat. It takes a lot of energy to pump water because it's bulky. Okay, so that creates inefficiency. But if you use another fluid, you can actually pump the heat down. Now, his idea is to do it on such a scale that you slow down global warming by preventing the heat building up on the surface. If you do it on a big enough scale, and that's the only really effective way we have for slowing down global warming at this point. I mentioned that the ocean is what's driving the system. This is not a permanent solution because it's slowing it down by putting the heat down to the deep water. Eventually, that's going to come back up. So we still need to balance the carbon cycle of CO2 at safe levels in the long run. It doesn't avoid the need to get off a fossil fuel economy and really start regenerating ecosystems the way they store carbon, which we know how to do. Biorock being one example of those many regenerative technologies. But Jim's idea is to do the ocean heat pumping to what he calls thermodynamic geoengineering. And his video is going to explain it. I don't know, Jim, if you want to explain a bit more, but let me just say that geoengineering has gotten a bad name because it's been associated with spraying sulfuric acid into space, which has all sorts of, we went through the acid rain in the 70s in Europe and North America. I hope we never go through that again. It seems madness to promote that. So unfortunately, that became the image of geoengineering. But we're now at the point of we're about to lose reefs. We're about to lose many other ecosystems. Reefs are going to be the first to go if we don't start doing something to affect heat directly. Now, we know how to stabilize the CO2 cycle, but it's not quick. We can plant trees, we can grow mangroves, we can generate blue carbon on a large scale with Biorock, but it's just not quick enough to avoid what we would call catastrophic overshoot or dangerous overshoot is what we're headed for right now. And so that means dealing with the heat itself directly rather than you've got to do the CO2 stuff and let it do its magic, but somehow you've got to deal with the heat at first if you don't want to have over. And that's what thermodynamic geoengineering aims to do. And I think, Jim, is that maybe you could say more?
Yeah. Okay, what can we do about that?
Can I share my screen?
Sure.
Okay.
Thermodynamic geoengineering, a solution to climate change and fossil fuel replacement.
Hey, we're not seeing this. We're seeing you, Jim. We're not seeing the video.
Okay. How do I?
Is there a share screen?
Yeah.
Yeah, on the bottom.
Yeah,
There
Okay,
you go. Looks like it started. Okay,
Okay.
there we are.
okay.
Mhm.
now we're seeing your home screen, but not the video. Okay, I guess you double click on that one, no?
There we are. Mhm.
Thermodynamic geoengineering, a solution to climate change and fossil fuel replacement.
Can you see that?
Yes. we
Yes.
can.
Is the
The
volume,
sound
the
is-
volume
the
seems
sound is-
low.
What's that?
I think the volume was a little low, Meta. Did you agree with that?
Yeah, I think we need louder, please.
Yes.
Okay,
Ocean heat, the essential measure of the Earth's climate. 93% of the heat of global warming is going into the oceans. In the tropics, this is thermally stratified in the ocean, with lighter water near the surface and denser water at greater depth. This configuration acts as a barrier to the efficient mixing of heat, carbon, oxygen, and the nutrients vital to aquatic life. Efficient mixing of these ingredients, as thermodynamic geoengineering provides, eliminates all risks of climate change while producing twice as much energy as is currently being derived from fossil fuels. A thermally stratified ocean lends itself to the conversion of a portion of the heat of global warming to work in accordance with the laws of thermodynamics and to the movement, through heat pipes, of surface heat to deep water where it is no longer any kind of environmental threat. Global warming is a problem of thermodynamics, governed by the laws of thermodynamics. The first law is the application of conservation of energy to the system and shows how energy, including global warming, can be changed from one form to another, but it cannot be created or destroyed. The second law sets the limits on the possible efficiency of a heat engine and determines the direction of energy flow, which is always from a region of high heat to a lower one. Geoengineering is a set of emerging technologies designed to manipulate the environment and offset some of the impacts of climate change. These technologies are typically split into two categories: carbon dioxide removal and solar radiation management. Thermodynamic geoengineering is the third way. It is the conversion of the heat of global warming to productive energy, as was first demonstrated by the Greek Hero of Alexandria in the 1st century AD with his Aeolipile. While Hero showed that his Aeolipile could lift a weight, in 1845, the English physicist James Prescott Joule used a falling weight to spin a paddle wheel in an insulated barrel to demonstrate how this mechanical energy raised the temperature of the water in the barrel. This equivalency between work and heat energy led to the formulation of the first law of thermodynamics. The thermal stratification of the ocean facilitates the conversion of a portion of the heat of warming to work in accordance with the first law. The process whereby the conversion of heat to work is accomplished is referred to ocean thermal energy conversion, or OTEC. It is one of the few non-polluting renewable energy technologies capable of delivering baseload power. But not all OTEC is created equally. With conventional OTEC, water is brought to the surface by massive pipes to condense a working fluid after it has passed through a turbine to produce power after the working fluid has been first vaporized using surface heat. The thermodynamic efficiency of this process is only about 3%, and the 97% of the surface heat diluted by the cold water is dispersed outward towards the poles that in the case of the Arctic is warmed 4 degrees over the course of 1,000 years at the same time as the tropics are cooled by the same amount. This upwelling approach is at least 2.5 times less efficient as thermodynamic geoengineering, which uses both warm and cold water contiguous to the evaporator and condenser, doesn't dump cold water near the ocean surface, uses pipes that are 1 order in diameter smaller, thus reducing the entire cost of the system by 1/3, pumps 1/200th of the fluids, and reduces the parasitic pumping losses of these fluids by 1/3. In their paper Quantification of Ocean Heat Uptake from Changes in Atmospheric Oxygen and Carbon Dioxide Composition, an international team of scientists calculated the amount of heat gain in the ocean between 1991 and 2016 on the basis of the amount of atmospheric oxygen and carbon dioxide released from the ocean as it warms. They found that the ocean gained on average 1.29 plus or minus 0.79 times 10 to the 22nd power joules of heat, which equates to 409 terawatts a year. In a 2007 patent filing, the experimental physicist Melvin Pruitt calculated an OTEC system like thermodynamic geoengineering, using a heat pipe to convey tropical heat into deep water could convert about 7.6% of the surface heat to work. 409 terawatts of heat converted to work at 7.6% efficiency produces 31 terawatts of primary energy, about 2.1 times as much energy as is currently being derived from fossil fuels. About a sixth of the world's electricity is currently produced by hydropower, which represents about 70% of our current renewable energy production. Hydropower exploits the energy potential of gravity, the same way Joule's experiment did, but in an open system, gravity is overcome by evaporation that converts surface water into vapor that rises to a higher elevation where it gains greater gravitational potential. The temperature differential between a tropical surface and a depth of 1,000 meters, where the temperature is universally about 4 degrees Celsius, has the same kind of hydraulic potential as the head of a hydroelectric dam. Each degree centigrade corresponds to a hydraulic head of 427 meters. Whereas the efficiency of a conventional dam is about 90%, the efficiency of thermodynamic geoengineering is about 7.6%. An OTEC map shows large areas of the tropical surface with a temperature of 30 degrees Celsius or greater, making a temperature differential between the surface and 1,000 meters of 26 degrees at 7.6% efficiency, equates to a theoretical head of 844 meters, which then has to be halved because thermodynamic geoengineering is theoretically an irreversible process, leaving a head of 422 meters. In reality, however, the diffusion rate of ocean heat from a depth of 1,000 meters is 1 centimeter per day through the deepest 900 meters of the ocean and 1 meter per day through the 100 meters of the ocean mixed layer. So, the initial unconverted heat is back at the surface in about 226 years where it can be recycled. In total 13 times, making thermodynamic geoengineering at 92.4% even more efficient than hydroelectricity. The tallest dam in the world at 305 meters is the Jinping Dam on the Yalong River in China. And China also has the largest hydroelectric facility, the Three Gorges Dam on the Yangtze River, with a hydraulic head of 80.6 meters and a capacity of 39.3 cubic kilometers. The Intertropical Convergence Zone is the best location for implementing thermodynamic geoengineering because it spans the equator and cyclones don't form there due to the self-canceling of the Coriolis effect as it switches from positive in the northern hemisphere to negative in the southern hemisphere. It has a width of about 7 degrees latitude and covers about 70% of the tropical surface for a total of about 28,000 square kilometers, or about 712 times the surface of the Three Gorges Dam, times 5.2 for the difference in hydraulic heads, equals 3,700 times the electrical potential of the Three Gorges Dam, which is estimated to cost $37 billion and has an installed capacity of 22,500 megawatts. Prorating 22,500 megawatts and $37 billion to the 31 terawatt electrical potential of thermodynamic geoengineering with its estimated cost of $2.9 trillion, as estimated and confirmed by Ron Bayman, Associate Professor of Economics at Benedictine University, and with the Healthy Planet Action Coalition, thermodynamic geoengineering is 17.5 times more cost-effective than the Three Gorges Dam. And although the Three Gorges Dam is for flood control and navigation purposes, as well as for power generation, a catalog of thermodynamic geoengineering benefits beyond power generation lists surface cooling, reversal of the off-gassing of oxygen and carbon dioxide from the ocean to the atmosphere as the ocean warms, the removal of cyclone fuel from the surface to deep water, the reduction of sea level rise due to thermal expansion of the ocean. The coefficient of expansion of seawater is half at 1,000 meters. It is the tropical surface, and heat moved into deep water is unavailable to melt ice caps, produce drought or wildfires. At a cost of $2.9 trillion annually, thermodynamic geoengineering is $3 trillion cheaper than the $5.9 trillion the International Monetary Fund has estimated is the environmental cost of doing business burning fossil fuels. Since 31 terawatts of energy produced with thermodynamic geoengineering would reverse the off-gassing of 4.3 gigatons of carbon dioxide from the ocean to the atmosphere, and since the notional cost of carbon dioxide removal from the atmosphere is $100 per ton, thermodynamic geoengineering would save the expenditure of $430 billion, which in combination with removing the environmental cost of burning fossil fuels, thermodynamic geoengineering is effectively too cheap to meter. At scale, it would produce electricity at a cost of 1.1 cents per kilowatt hour. Wind and solar are promoted as the best renewable energy resources for replacing fossil fuels, but the U.S. National Renewable Energy Laboratory has determined that the total useful surface area for a wind farm is about 250,000 square meters per megawatt of power, and for photovoltaics it is about 16,000 square meters per megawatt. Considering thermodynamic geoengineering would produce 200 megawatts of OTEC from 10,000 square meters of the ocean's surface, it is a 300 times greater solar concentrator than conventional photovoltaic devices. The U.S. Energy Information Administration says energy heat pumps, powered by low emissions electricity, are the central technology in the global transition to secure and sustainable heating. They are currently available on the market and are 3 to 5 times more energy efficient than natural gas boilers. They reduce householders' exposure to fossil fuel price spikes and can provide cooling as well as heating, which is responsible for 4 gigatons of carbon dioxide emissions annually, or about 10% of all emissions. Like a heat pump, thermodynamic geoengineering moves heat through the phases of a low boiling point working fluid. But in the latter case, this is a free ride. Furthermore, the hotter the ocean surface gets, the more energy thermodynamic geoengineering produces and the more efficient it becomes. An evaporator at the surface passively boils the thermodynamic geoengineering working fluid, producing a pressure that allows the vapor to flow into the deep, cold water at a velocity approaching that of sound, where the vapor condenses to a liquid that is pumped back to the surface to complete the cycle. This vapor flow is interrupted by a heat engine that changes the work into electrical energy with a loss of only about 4.8% in pumping losses incurred, returning the condensed working fluid back to the surface. In other words, about 12 times more energy is produced by the system as is consumed internally by the pumps. Heat pumps typically use about 5 times less energy in the cooling mode than in the heating mode, because in cold weather there isn't as much heat that can be absorbed from outside the system. Since thermodynamic geoengineering is always in its cooling mode, it is a highly efficient way of cooling the surface, in part because there is always a lot more cold water in the oceans than hot water, which in the latter case is the principal threat from global warming. The final obstacle that must be overcome in order for thermodynamic geoengineering to bring about a transition away from fossil fuels is the availability of raw material. The oceans contains 47 minerals and metals dissolved in solution, some of which are already being harvested. Thermodynamic geoengineering platforms harvesting surface heat to produce energy would pass millions of tons of water through their heat exchangers, which could be adapted to extract a portion of the 50 quadrillion tons of trace elements that are dissolved in solution in the ocean. For example, 31,001 gigawatt thermodynamic geoengineering plants would move 124 million tons of water per second through their heat exchangers, which means the 1.45 quintillion short tons of water, the total mass of the ocean's water, will be shifted to these heat exchangers in about 370 years. The concentration of magnesium, currently valued at between $12,000 to $15,000 per ton, is 1,272 parts per million, about 3 times the concentration of carbon dioxide in the atmosphere, which it is notionally being contemplated should be removed from the atmosphere at a cost of about $100 per ton. The method of precipitating magnesium from seawater has been known for over a century, and magnesium alloys reduce the weight of heat-removing elements like heat exchangers used for thermodynamic geoengineering by a third without losing its heat-transferring properties. At 1,272 parts per million of the 1.45 quintillion short tons of water in the ocean, the current cost of the metal would be reduced by several orders of magnitude when produced as an adjunct to thermodynamic geoengineering energy-producing operations. In short, thermodynamic geoengineering is the hybrid heat pump, heat pipe, heat engine, holistic approach to the problems of global warming and fossil fuel replacement.
Wow. Okay.
Jim, did you have something more you wanted to say or present on the larger scale applications of this concept?
Well, you say it's a temporary solution. I think that's totally wrong. I mean, the heat of global warming is 408 terawatts, and all we're going to produce is 31%. The heat we send into the deep is going to return in 226 years, and then that heat again can be recycled 13 times until all of the heat of global warming is consumed.
Well, I think what's really important about this method is it's a way of moving the heat down. I mean, that's really the key thing. That slows down surface warming, which is out of control and which is accelerating sea level rise. And we have meters of sea level rise ahead of us. People don't realize how serious that is. So all of the other forms of sustainable energy do not help cool the ocean itself. I mean, I think that's the key thing about this technology, but it would have to be applied, as Jim says, on a large scale. Now, so he's envisioning, I think, fleets of floating systems. Now, floating solar panels could also be part of that, for example, because we know now that there's big investment in floating solar panels. I mean, I said I'm involved with projects in Kiribati and Tuvalu, but the Maldives, I'm also involved with projects there. Asian Development Bank is planning to do them in 11 Pacific countries. So there's going to be serious investment in that. But now, these are mostly, they're looking for areas in protected lagoons. But now what Jim's thinking about is more out there in the open sea, because you're trying to get above the deep water. One issue with the small island states is that they have vastly greater areas of ocean than they have of land, vastly greater. And so the small island developing states are now recasting themselves as large ocean states. And the fact is that they're not getting very much out of those large areas of ocean at this point, because what they're doing is leasing it to foreign tuna fleets who are simply taking everything they can take. I mean, so it's the usual destructive overfishing mode. That the countries get a percentage of what's reported, but that's grossly underreported. So they're really running their own coastal ecosystems down. But if they're making energy in those areas, they have large areas of ocean that they could be using to have, for instance, floating reefs. For instance, with BioRock, we could make floating reefs, in a sense, upside down, that would attract fish, tuna, mahi-mahi. All these fish love shade. But I mentioned that coral reefs are limited.
By the way, I've talked to Brian von Herzen about his plan to use floating fish farms for kelp. Which would attract fish and so on. But to do that, he needs to bring up, he needs to pump stuff up. So I think he uses some sort of upwelling pump to bring up cold water, but it also brings up nutrients.
Mhm.
And that's what's required. That, I take it, is almost the opposite of what Jim is proposing. Is that right? That Jim, you wouldn't be of any value to him with your technology wouldn't work. Is that right?
Yeah, no, it works. It just takes a long time. It takes 226 years for the heat to come back to the surface.
Okay.
See,
Well, I wish
excess
we-
nutrients, let me just say this, sorry, excess nutrients in the coastal zone is a real concern. You don't want people doing this near reefs because you're going to cause algae blooms that will kill the reefs. So, you know, I'm very wary of a lot of proposals to increase upwelling in places that are going to be ecologically harmed by it, because we're seeing that happen in many places. So now the thing is, you know, coral reefs, as I say, are limited to a very small area, shallow water, but we can now grow them out over deep blue water if they're floating and linked to something like.
Okay, all right.
Oh yes. So that's one thing we're looking at with the atoll countries, because to find a way to enhance the quality of their tuna habitat and their populations by making floating habitats in their territorial waters. So that's definitely one of the things we're looking at. So I think that could be linked to thermodynamic geoengineering. I think, Jim, your view is that these things would not be fixed to a given location. They would move around.
They have to, you want to move to where the water is hottest, which is seasonal. So
Yes.
you're grazing the oceans to find the hottest waters.
Mm-hmm. Mm-hmm. And avoid hurricanes
You know,
too.
I think we're gonna need
they-
a whole new, because we've gone way over time.
Okay,
And
so
I feel we're just getting started. So I think we're going to need another session to explore this in not only in detail, but in language that I and ordinary mortals can
Well-
understand, who are not engineers or scientists.
That's where I would be. I would hope that Dr. Buckley has a look at this, because I mean, the physics and the engineering of it are right up her alley.
Well, I will absolutely call her attention to this. I could have brought her on, but actually it doesn't matter, because we jam-packed this whole conversation. It's really full of gems that I'd like to explore further. So if you're willing, I'll set up another time and we'll have another go at it, because our time is way up now, but I do want to explore this further, enough so that I can understand it fully if possible. Okay?
yes,
Okay.
you know, I think if you can get to the other people who weren't able to join us today, that will be a very interesting session there.
All right, we'll do it.
Yes.
Thank you so much, both of you. I've enjoyed every minute of it, and I'll watch it 2 or 3 times over to make sure